All right, this week we're going to introduce our Lab 5. So within this lab, there's going to be 3 different weeks associated with the experiment. There's going to be Lab 5A, Lab 5B, and Lab 5C. So in the first week is going to be the heat treatment of the tensile specimen. So there's going to be 2 types of materials that we're going to test within this. It's going to be aluminum 6061 and our steel 4130, which is going to be annealed, quenched, and then tempered. So then during our second week, what we're going to do is we're going to do our tensile testing. And in the third week, that's when we're going to get into our SEM surface analysis of those test specimens. Let's talk a little bit now about our experimental goals for this week, this lab. So the goal of the Lab 5 experiment is to have exposure to the standard testing using a servo hydraulic testing machine. So we're going to be using the Instron machine, in particular the Instron 8801, to be doing our tensile testing. Now, from there, what we want to do is we want to analyze the testing results. So we're going to plot our stress and strain curves for the different materials from the experimental data. Now, from this data and analyzing the stress strain curves, what we're going to do is we're going to back out our material properties. So if we refer back to ME 101, our materials engineering class, we talked about how we do this and some of the key equations we utilize for this. So week 1, again, is going to be the heat treatment of our tensile specimen. And then from there, we're going to go into week 2, which we're going to have 2 parts within week 2. The first part of week 2, we're going to perform the testing on our 6160 aluminum specimens. And then in part 2 of week 2, that's where we're going to move over to our 4130 steel specimens and study the effects of the heat treatment process on these as well. And lastly, for week 3, we're going to take these specimens that we tested and we're going to take a look at them on the SEM microscope for fracture surface analysis. So we're going to talk a little bit now about the standards that we're going to be utilizing with this experiment. So what we have to understand is there are going to be some specified ASTM standard methods for tensile testing specifically of metallic materials. So we can reference these standards, which again right here is our E8/E8M09 standards for our tensile testing of metallic materials. And there's also an ISO standard as well, our ISO 6892-1 is for metallic materials for tensile testing, part 1 again. So the title of this is going to be the method of test at a room temperature. So make sure when we're selecting our standards and following them, we select the correct ones for the types of tests that we're running, as well as the materials that we're going to be utilizing. So we're going to take a little bit of time here and discuss the material testing machine itself. So when we're talking about a material testing machine, there's a couple different types that we can utilize. 3 main types here. We have a screw drive that controls the motion up and down. We have hydraulic systems, and then there are a few other ones, piezoelectric actuator, and these are for lower loads and higher resolution type of applications. So these are the 2 main ones we would use for a tensile test of the metallic specimen that we're using here of the size that we're using as well. There's a couple of bigger, older Tenias-Olson machines that use the screw drives down in the basement of ODI. We have a newer one here, the Instron machine that we'll be using for this test. Couple different methods now if we're talking about measuring the displacement as we're running the test. So we can see if the crosshead itself is moving up and down, a lot of times internal to the machine, this will be captured for this displacement here, and we can say, okay, the crosshead has moved up this amount of distance, so therefore our specimen has a displacement associated with the head movement. Now the other way that's a little bit more accurate is we can clip on an extensometer onto our testing sample. And when we clip this on here, it gives us a little bit higher resolution, especially if it's smaller deflections and displacements. This extensometer is great to have. And a lot of the tests that I've run when we're doing some tensile testing, material testing, I've used both of these. This is a double check from one against the other. A lot of times you have specimens you can't replace. You really want to make sure that that setup is completely accurate and you're recording all the data that you need. So this is a great double check to use both of those in order to determine the displacement. Now, if we talk about displacement measurements, we can also talk about how to measure the load. Almost all these machines are going to have an inline load cell in there, so this is all going to be internal. So how you set it up, the units you set up, resolution is going to be dependent upon that. Some of the older systems and in newer systems, you can switch out the load cell, higher load cell, so you can get up to larger loads, but maybe the accuracy isn't there. So make sure you choose the appropriate load cell and fit it with the machine before running your tests. So the last thing we're going to discuss here as far as the testing machine goes is the method to control the load. So you can do displacement controlled or you could do load controlled are the two primary ones there. So this one right here, we're doing a load controlled feedback. So we're saying increase by a pound each time. Whereas a displacement control, we would say move a fraction of a centimeter, a millimeter, for each of the steps. So that's the difference between our load control and our displacement control of our system. So we are lucky to have a newer servo hydraulic testing machine here. So this is the Instron 8801. We can see over here. And we can see within this here, there's a couple of key components. You have your computer system over here to program everything and control it, connected over to the testing system and you can see you have two different heads here with two different grips on this in order to connect to our specimens. A little bit closer, again, you can see the two grips here, so your specimen is going to fit right into these two grips. Just make it nice and easy. And then, again, we write our whole program as controlled by the PC. So your load rates, displacement, data acquisition, all of that is pre-programmed in and on the PC. Now you can see off to the right over here, you can also manually control this as well. And a lot of times we'll use the manual control for initial setup to get everything just about right in position, re-zero, set our home position, and then switch into our program. So this again was a hydraulic system here, so we can see a lot of this all set up underneath if we were to open up the cover under the testing machine there. So what's really nice about this is it has a hydraulic grip. Now some of the older systems have a mechanical grip where you just tighten as much as you can, and then as the test specimen pulls, it locks in and grips the teeth. And a lot of the issues that we've had with some of these older testing machines that use those style of mechanical grips there with just the teeth on it is that it slips a little bit. So your displacement might be off a little bit. It may damage your test specimen a little bit. Whereas this one here has a really nice hydraulic grip right here, and you can see the hydraulic line coming in. So your specimen gets in there, gripped really nice and tight, so you don't have to worry about the slipping. And then we come over here to the right thing, and this is where we talked about adding the extensometer onto it, our test specimen, in order to get a little bit more accurate displacement. So you can see it clips right on here to our test specimen. This is a round specimen in this one here, but we'll have a flat specimen. And the difference is sometimes the little grips on the end we need to swap out based on what specimen shape we're utilizing here, and this will accurately measure the deflection in just the specimen itself. And going back to talking about our grips, if for some reason our grips did slip there, that's not going to be affected by the displacement between these two here. So even if it slips in these grips a little bit here, our displacement is still going to be accurate. So again, that's why I really like to record both the crosshead displacement as well as the extensometer displacement as well, just as a double check in case something goes wrong in your testing. So now that we've talked about the testing machine, now we're going to take a look a little bit more at the actual specimens we're going to be utilizing for this test here. So these are going to be called as what are known as dog bone specimens, and it comes from their shape. They are shaped somewhat like a dog bone here, and there's a reason why we do that. And this is something that's actually called out by the ASTM specification for this testing. So one of the main things, this is going to ensure that the fracture region is going to be in the center section away from our grips. So this right here and this right here are the two grips of our specimen that go into the grips that we saw on the hydraulic testing machine. And this is the center section right here where we want the fracture to occur. Now this shape right here is going to reduce the stress concentration at the grips, and you can see we don't come in at very sharp. That's going to increase our stress concentrations if this right here was really sharp. So we do this nice rounding in our specimens here to take it away from that region, which would be a high stress concentration area, and direct it back down here in the center of the specimen. So again, for our specimens, we're going to do this with 6160 aluminum, and this is going to be cast. And this is the other specimen we're going to use is a 4130 steel, which is hot rolled and annealed. So once we run the test, we put these dog bone specimens into our material testing system, run the test, get our data. We need to determine the structural properties from the data that we have collected. So first thing we need to do is when we're running the test, make sure that we set it up in the correct way to measure our load and our displacement. So those are two of the things. I would also measure your time as well. You want to make sure that your displacement rates are correct. So with this, when you're setting up your system and writing your program there, you really want to make sure your load, displacement, and time are all collected. Now, some systems also allow you to collect your stress and strain directly. So we can either calculate it afterwards or collect it directly within the system. And I honestly would suggest doing both again as a double check. So with this, what we want to calculate is our stiffness and flexibility, our ultimate load, and our maximum elongation. So again, what we can do is take a look at the shape of our test specimen. So in that center section of it, it's going to have a known cross-sectional area. And this is what we're going to use in order to determine our stress and strain calculations for this here. It's going to be based upon this geometry right here. So this, along with the length of the specimen, are going to be crucial as we're setting this up. And a lot of times they'll ask you within the program, okay, what specimen are you using? Is it flat? Is it round? What is the diameter? What is the thickness? What is the length? And all that information can be input, and it'll actually give you in your output of your data, it might give you another column, say this is your stress, this is your strain, this is your maximum elongation, this is your load at break. Or we can do it by hand manually as well and just collect our load, displacement, and time and take a look at all this information and do our post-processing. Like I said, if the system does give you the option to do it internally, I would do both. Take a look at the raw data, calculate it yourself, and also take a look and see what the system does for your calculations for you. So let's take a little bit closer look at our tensile specimen here, or our dog bone samples here. So again, this is something that's specified by ASTM by the name of it. We've talked a little bit about this, but I want to get into a little bit more detail on the manufacturing of these. So what we have here is you have a straight piece of metal here, whether it's your steel or your aluminum here, and you need to machine out this shape in it to get our good center section here, where we're getting rid of the stress concentration up here, a nice round in that, nice radius there, and the grips are going to have the right length to fit into your system. So as you're designing these out for specific systems, you really want to make sure you pay close attention to the dimensions. Now, whether you're doing this on a manual machine and you're programming in your G-code, or if you draw this all out in SolidWorks, have a 3D model and you feed it into a programmable CNC, either way, you want to make sure that your dimensions are correct for everything there and you have your machine set up in the correct way. So we can see down here, here's one that's been machined out for a dog bone specimen there. We have nice long grips that are going to fit into the machine. We want to make sure that this length is the right length here that we need for our testing and our calculations. So again, this is the purpose of these radiuses to ensure that it breaks right at our center section right there, and we're going to be doing this for our specimen for 6160 and 4130 for both of these. So as we're talking about machining these test specimens, this is something that's going to become important when you're setting up your machining. So if you have the wrong speeds, the wrong bit, the wrong feed rates, the wrong depths, all of this stuff in your manufacturing could lead to some machining defects that we see right here. And if these are big enough or frequent enough within your test specimen, this can lead to stress concentrations that can impact the actual testing results in our tensile test. The idea is to have this perfectly smooth, perfectly uniform all along that center section there so that we're testing just the material there and we know the exact cross-sectional area. So if you think about it, if these are deep enough, that technically is going to change the cross-sectional area in that point as compared to the rest of it here, and we don't want that to happen. So how you set up your machining, again, whether you're doing it manually, hand cranking it through, G-code, or feeding in a SolidWorks model, we really want to make sure that how you set up your feed rates, your speeds, your bits, and all of that stuff is going to be accurate to give us a nice smooth surface here on the test specimen. So another thing I want to talk quickly about here is the difference in our surface finishes of our specimens and how that could potentially affect our tensile fracture here. So I'm going to take a look at these three pictures here, and what you can see is on the left-hand side over here, you see a little bit of necking going on there, and this is from a milled specimen. Whereas over here on our cast specimen, it's a lot cleaner break, a lot less necking going on the cast specimen over here. Taking a look at it from the side, again, you can see this kind of drawing out here, tapering and necking occurring. On the milled specimen, where you don't see it, it's more of a clean fracture break right there. On the cast specimen there. And then a little ISO view as well, showing it one last time down here in this picture. So again, you see that necking, and then over here you're seeing a real brittle fracture right here on the cast. So necking for the milled and a brittle for our cast specimen. So now as we begin our calculations, when we're talking about our stress and our strain that we need to calculate here, again, sometimes this can be done internal, but we're going to be doing a lot of this by hand calculations from our raw data. If we talk about our engineering stress right here, here is our governing equation. Our engineering stress is equal to force over our area, our A naught here, our cross-sectional area of our test specimen, and the load is what we're going to be collecting from our data on our tensile testing machine. And we're talking about our strain here. Well, our strain here, our engineering strain, is equal to the deflection over our initial length here, or our final length minus initial length, or our change in length over our initial length right there, is going to give us our engineering strain. So again, these are things that are going to be in our raw data that we can collect. We're going to know and measure our initial length, or L naught, and we're going to be having our final length here, or our length as it changes as we stretch our test specimen and pull it, of our L here that we collect in our data. So what we want to do with this data is take a look and graph it here. And when we graph it, we're going to have our strain as a percentage down here on our x-axis, and we're going to have our engineering stress up here in units of MPa on our y-axis there, and we're going to graph our stress versus strain right here, and we can see this curve coming up. So this is a typical curve that you guys should expect to see with your data here for the tensile test that we're going to be run. Things again to pay attention to is your units. This is going to be in percent, and this is going to be in MPa there. Make sure when you're doing your calculations out, you have the correct units before you plug them into your graph. So the next thing we want to do is do a little bit of analysis on this stress strain data from our graph here. So again, same graph, we have strain on the bottom, stress on our y-axis over here. Now what we can see, we have a couple things within this that we're going to look at. One is going to be this proportional limit up top here, right where we kind of come out of this elastic region up here and it starts to fail. So this is where our test specimen starts to fail right here, proportional limit right there. And our slope right here is what we're going to be referring to as our elastic modulus. This is going to be important to back out some of the material properties of our test specimen. So another thing to consider here is we're going to have a 0.2% plastic strain offset method that we're going to utilize here. So we can see we shift this over right there to account for that plastic strain offset method right there. And then what we have is this new intersection right here where this now intersects with our curve up top here. This is what's going to be known as our yield stress. And again, we come over here at this point, we come across over here, and we can figure out, okay, this is my yield stress. And we can drop right back down here and figure out our strain for that yield stress as well. So another important thing that we want to get from our stress strain curve here is the stress at where our specimen actually fails and breaks. So the stress at where it breaks is known as our ultimate stress right here, our failure stress right there. And you can see as we're coming up and we get to right here at this point, it drops right away. So that is where the stress, the specimen itself actually breaks. So again, our ultimate stress right there. So another thing that we can determine from our stress strain diagram here is our modulus of toughness. Now this is the material's ability to absorb energy in plastic deformation. So it's going to be defined as the amount of strain, energy density, which is strain on a unit volume of material. So you can see there's our volume over there on our graph, that a given material can absorb before it fractures. So the thing to note about this, our units that we're going to utilize with this is either going to be PSI or in pascals. So the next thing we want to talk about here is necking. We'll take a look here for a constant volume. So we have this key equation here. We have our A naught times our L naught, which is our initial cross-sectional area and our initial length. This is equal to our final area here after deformation times our L. This is going to be L naught plus our change, our deformation of length right there. So this can then be written as over here to the right, when we place the right-hand side of the equation, our A sub F, cross-sectional area after deformation, times our L naught initial length, times the ratio of L naught over L naught times our delta here. And this is just doing a little bit of math manipulation so that we end up with down over here. This is going to give us a replacement here for our strain within this here. So we can say that A naught times L naught is equal to AF L naught times 1 plus our engineering strain right there, 1 plus our epsilon. So from this here, we can then rearrange this a little bit more, and we can say, okay, if I want to solve this just for my AF here, I can calculate my AF to be my A naught, my initial cross-sectional area, divided by 1 plus my epsilon value right there. So therefore, we can say that our area ratio, our A naught over our AF here for our area ratio, is equal to our 1 plus epsilon. So the next thing we're looking at here is our true strain. Now this is defined as the change in length divided by the length existing immediately prior, right before the last small strain step. So how we come up with an equation for that right there is our true strain, our epsilon sub t here, is equal to summation from our initial length to our final length here. And here is this change in length divided by existing length, so delta L over L. So this is equal to our integral with the limits of integration from L naught to LF of that dl over L for this relationship here in order to calculate our true strain. So we can reduce that down a little bit, and this would be when we do out our integral right here, do out the calculus, this is the natural log of our r that we just defined on the previous page, that ratio, which is then equal to the natural log of, we defined r as 1 plus our epsilon, so we can plug that in here. So this is how we are going to determine our true strain. So next we're going to take a look at our true stress. We've already talked about our true strain. Our true stress here is going to be our stress affiliated with our cross-sectional area. So our equation here for true stress is going to be that load P divided by our A sub F, our cross-sectional area after deformation. And we have a definition here for our A sub F. A sub F is equal to our A naught divided by 1 over our strain, or our epsilon value there. So we can plug this relationship back in now for A sub F. And when we do that, we plug that back in here for our A sub F, and we end up with our true stress here, our sigma sub t, is equal to load over our A naught times 1 plus our epsilon value right there. So then we can plug in, rearrange this just slightly here, and we can say, okay, this is equal to, now if we have this P over A naught there, that's simply our sigma. So that we can plug back in for our sigma there. So sigma t is equal to our stress here. So our true stress is equal to our stress times 1 plus epsilon, where we've found that our 1 plus epsilon is equal to our ratio r right here. So therefore, our true stress is equal to our sigma r by this relationship here. So let's talk a little bit about the procedure for our experiment here. So in this lab demonstration, we're going to talk about the heat treatment of our 4130 steel. So the first step in this process of heat treating this specimen is to set our oven temperature to 925 degrees Celsius. We're going to maintain this for an hour plus. Then when we remove our specimen, we're going to rapidly quench it in a water bath here. So here's our specimen right there. We can see the person has a protective glove on and our clamps here to take it from the oven, put it into our water bath, quickly quench it. Now one thing to notice over here on the right is you're going to see some of this scaling. Right after we take this out of the quenching, you can see the scaling there, and this is right on the surface of our specimen, and this is a result from oxidation. Let's take a look at our IT diagram, or our isothermal transformation for 4130 steel. So what we can see here is in this graph down here on our diagram, we have our temperature over here on our y-axis in degrees Fahrenheit and Celsius as well. And on our x-axis, we have our time in seconds. So now when we quench our sample here, we can produce martensite along with some ferrite and cementite. The martensite is what's going to harden the surface of our specimen. And this is due to the fact that we have chromium and molybdenum in our structure, which contribute to the hardenability of the steel. So as you can see from this chart here, you can look over on the right-hand side of our y-axis here, and we can get our hardness values as well. So now we're going to take a look at our hardenability curve for our 4130 steel here. So we can see down here, here's our diagram down here. We have our hardness over here on our y-axis on the left side going from 0 here up to 60. We have our distance from the quenched end in units of 1/16 of an inch, starting at 0 here. So a 0 distance from our quenched end right there, all the way up to 40 over here. And on our other y-axis here on the right-hand side, we have our percentage of martensite. Now we recall here that our surface is going to be hardened by our martensitic transformation. That's going to lead to the hardening of our surface. We can see over here, we can have our makeup of our 4130 over here, given by our information shown here. And we have here that our temperature at 1550 degrees Fahrenheit, and our grain size over here is going to be between 9 and 10 for this case. So as we continue on looking at our heat treatment of steel for our specimens here, we're going to take a look at the crystal structures for different phases of steel. What we're going to do is we're going to go over the transformation occurring during our quenching. So at 925 degrees Celsius right here, we have the fact that austenite will be produced. So when we heat it up, we're going to produce our austenite when we get to 925 degrees Celsius. And this is going to be an FCC structure right here, face-centered cubic. Now, if we were to take and cool this very slowly, then some ferrite will going to form right here. So this is going to be a BCC structure right here for the slow cooling to produce the ferrite. What you can see here is our carbon atom, and this one is completely segregated or diffused from our cementite. Now for rapid cooling, we'd have a BCT structure over here, and with this structure right here, we have the formation of martensite. We notice here now is our carbon atom does not have time to leave the structure. So as we continue on here, we're going to focus on martensite here, and we're going to talk about the impact of tempering. So martensite, as we recall here, is going to be very strong and hard, but it's also going to be brittle, and that can be an issue. So we can think about now is tempering. So this is a post-processing heat treatment used to recover some of the ductility. So if it's really brittle, we might be able to recover some of that ductility. Now tempering is going to be a diffusion-based process. Carbon atoms were formed at an elevated temperature here. We have 250 to 600 degrees Celsius. So we can see this process illustrated below. There is our martensite, and then we do this tempering process here with heat and time. We end up over here with our dual phase over here that we can see in this diagram or this picture right here. So by increasing our particle size here, this is going to reduce the boundary area, and this is going to help determine the amount of ductility that can be recovered. So this particle size determined by diffusion versus time here is shown in the graph below here. So we have time on our bottom x-axis here, and we have our hardness in our C values over here, and our Rockwell scale and our Burnell hardness scale over here on the right side. And we can see time in seconds on the bottom. On the top, we can see it in minutes, hours, and days here. And what we're seeing happening is the time increases, the hardness is going to slowly decrease over that amount of time. Now, this diffusion process can be accelerated by increasing the temperature. So let's take a look and see the difference between the load and displacement curve we're looking at here for an untreated sample, a tempered sample, and a water-quenched sample. So what we can see is our load is on our y-axis here, our displacement's on our x-axis over here. So let's talk about the untreated first. So we can see this ramps up almost linearly up to here, which is just about, a little over 0.1 inches and just under 4,000 pounds here. Stays pretty much in the linear region there. Then we can see quickly curves off, and it doesn't break or fail. It just stays there and stretches, and you can see the displacement increases and increases all the way out here to almost 0.8, 0.9 inches before it actually fails and the specimen breaks. Whereas if we have a water quenched one here in red, we can see this keeps going up. Pretty much follows that same curve at the beginning, but then it keeps going up when it's water quenched. We get a higher and higher and higher load. Right here, we get up to over 12,000 pounds here, and then it quickly fills off there. Whereas our tempered one here, we can see it does change the curve slightly here, shifts it over to the right, a little bit more displacement, a little bit more elongation here, and not quite as strong here as we were just about 1,000 before it breaks off there. And this was tempered here for an hour at 400 C. So how does this look when we actually compare the specimens for all those? So here's our actual sample here, our standard sample right there as our baseline. Now our non-quenched, we can see this was a lot longer if we come off the end of here. Displacement, distortion of this as it stretched before it broke there for our non-quenched, whereas our quenched one we have right here, and our tempered one we have right here. So we can see our quenched, the break style there, and the break style here with our tempered right there. Not a huge difference in the overall length, but what we'd come to expect from the previous graph between our quenched and our tempered steel samples. So the other thing to consider here is our fracture surface of the microstructure. So we're going to take a look at this under a scanning electron microscope. So even just a close-up, not even high resolution, is medium resolution photo here, we can see the difference here between a brittle break and a ductile material here. So you have a brittle material over here on the left, and you have a ductile material over here on the right. You can see a little bit more necking going on with the ductile material, and you can see how it stretches before it breaks, whereas the brittle one just snaps almost clean through. And we zoom in at that, and you can see the cleavage facets right here in this brittle material on the left, whereas you're seeing more of these voids over here on the ductile material on the right when we're looking at it through a scanning electron microscope. So as we continue looking at the fracture surface here at the microstructure here, this one, in this particular case, is for 6160 aluminum. It's air cooled, but we can still see for this ductile material, you're seeing in this image here, you're seeing these long grains and the dimpling within the image here. So that's something that we're going to see for any of these ductile type of materials when we look at them under a scanning electron microscope. Now if we continue on here, we're talking about a 4130 steel here that's ductile. This is what this is going to look like here. You're going to have these larger voids, the dimples you're going to still see there, and you're going to have some sheared ligaments here. So that's what you're going to look like here for an air-cooled 4130 steel when you're looking at it through a scanning electron microscope. So now we'll move on to a water-cooled 4140 steel sample here under the scanning electron microscope. So there's a few small voids over here, but lots of large cleavage facets here. So this is going to be what we're going to call a quasi-brittle material here, because you are still seeing some of those smaller voids there, but you're still seeing a lot more leaning towards the brittle side with these large cleavage facets. So lastly, now we're going to take a look here at our 4130 steel that's been tempered here. So there's a few facets here and lots of small voids, so we're going to call this quasi-ductile. So it's going to be some of the properties of being a little bit more brittle, but it's really leaning toward the ductile side over here by looking at all the structure here under the scanning electron microscope.